Now, towards the end of the chapter, we're going to discuss some very nice class of OX modules, which are particularly easy to handle and which have nice properties. And as inspiration, well, if we think about the R modules in the commutative algebra world, the easiest class of those are, of course, the free R modules, which are just some direct sum of R itself. And if we have quasi-coherent sheaves F on X, then locally we are given by such a R module. And so the idea is just to say the following definition. If you have F quasi-coherent OX module, we call it locally free if, well, locally on such a cover, you are given by such a free R module. So in other words, there exists an affine cover by the spec Ri, such that F restricted to the elements of this affine cover is the quasi-coherent sheaf associated to a free Ri module of finite rank. And if the rank is the same for all of these Ui, then we call it actually the rank of the sheaf F itself. One note here is already, this is one case where it's not true that we can replace this existing affine cover by any affine cover. So in this case, it's actually important that it's just necessary that there exists some affine cover. It's not true that for any affine subset of X, this is actually the free R module over this spec R. So some remarks. So if we have, it's certainly true that F restricted to these Ui is basically by definition, because if Mi is a free Ri module, then Mi is of this form Ri to the n. And then if you take the tilde, well, the R tilde gives you O Ui. And so if you take some number of copies of this, you get O Ui to this power. But it's not the case that necessarily F is already given by OX to this power on all of X. So even though on these open subsets this is true, it's not the case necessarily that this is true everywhere. And we have already seen such an example, which is kind of the most interesting first example that you can look at for these locally free sheaves. Namely, on X equals the projective space Pn, we saw these twisting sheaves OPn of D. And the first claim here is that these are locally free because on the standard open cover by the UIs, we have written down explicitly in isomorphism from this restriction to just OUI, which is OUI to the power 1. And so somehow this means we have this affine cover by the UI on which this is trivial. So sometimes you also say this is the trivializing cover for this locally free sheaf. And so by definition, we have checked this property. So this thing is locally free. And actually we see that on all elements of this cover, we always take the same number here. The rank is always 1. And so this is in fact locally free of rank 1. But something which we have also seen is that it's not true that this OPn of D is isomorphic to OPn when D is not 0. Because, for example, we can look at what the global sections on Pn are. So here the global sections of OPn, these are the regular functions on all of Pn. And that we have seen a long time ago, this is just a constant function. So this is one-dimensional over whatever field we work in. But on this side here, we saw that when D is positive, then D's actually have a lot of sections. So this is the space of all homogeneous degree D polynomials, which is always greater than one-dimensional when D is at least 1. And on the other hand, when D is negative, we saw that this thing doesn't have any global sections at all. So in both cases, it cannot be true that these things are isomorphic. So this is our first example of something which is locally free of rank 1. In fact, it's locally a trivial sheaf, just OU, but it's not globally such a free OX module. So it's not the case that it's just isomorphic to OPN. Okay, so this was the first example. The second, connecting back to what we have seen about the fibers of sheaves. Actually, the fibers of locally free modules are particularly nice. Namely, if F is locally free of rank R, then the claim is its fiber at a given point is just an R-dimensional vector space over the field associated to this point. And the reason is just that this point has a neighborhood by definition. We find one element of this open cover on which the restriction of F is just given by this thing here, right? And then we can do the same trick that we saw last time. If we want to restrict to P, we can first restrict to this open neighborhood on which we get this direct sum of trivial structure sheaves. And then we restrict to P. But then when we restrict this thing here to P, we have seen the pullback of O is actually just O. So the pullback of OUI to P is just OP. And so we get just OP to some rank, in this case rank R. And the global sections on a point of O to the R are just some k to the point to the power R. And so this explains why we get this vector space here. And the geometric perspective on these locally free sheaves is then actually that you can see them as this kind of collection of fibers over all of the points. If the point starts varying in X, then for each of those you get one of these vector spaces, and there exists, you can kind of put them all together. So there exists a scheme, which is called the total space of this locally free sheaf. And it has a map down to X with the property that, for example, the pre-image over a point P is exactly a vector space, which is this F, the fiber of F at the point P. And so these vector spaces fit together nicely. They form this total space of F. And then it's true that you can construct this total space in such a way that the sections on any open subset U of X, then on the one hand, of course, you can just write down F of U, right? This is a sheaf, you have an open subset, you get a set of sections. But you can arrange it in such a way that this is also the set of morphisms from U into this total space, which are really sections of this morphism, in the sense that if you compose this S with the projection pi down, you get the identity on U. So this is the second perspective. And the idea, how does this work? How can you get this total space? Well, there's one case in which it's easy to write down such a total space. Namely, if you are on an open subset UI, where F is actually just restricted to this UI, is just this direct sum of structure sheaves, then there the total space of this trivial vector bundle here, sorry, this trivial locally free sheaf, you can just take to be UI cross the affine space AR mapping down to UI. Why is that? Well, what is the section of this morphism here? You have to give a map from UI to itself and the map from UI to A to the R. And being a section means if you take the projection downstairs, you must get the identity. So this forces the map from UI to itself to be this identity. And so the data of the section is just a map from UI to A to the R itself, which are just R functions. But the data of R functions are also the same thing as the sections of this sheaf OUI to the R. So there's kind of an equivalence between these sets here, which is exactly this equivalence. So somehow on these open patches, which where the curly F becomes trivial, on these, you can take the total space to be just this product. And then the idea to get the total space for F is just that, well, these UI cover X. So on those, you know what the total space is, and then you can glue them together. And there's a natural compatibility condition there. So you can glue them all together, and then you get a scheme like this. So gluing for schemes, we have already seen several times, still works if you do it, if you make sure that you're compatible on the overlaps. And so you get the total space, and this is called a vector bundle. So whenever you have a locally free sheaf, then you can always think of having this kind of vector bundle around. And if you have maybe taking some class in differential geometry, then you will probably also have seen these vector bundles like this. An even nicer case, so being locally free is already nice. An even nicer case is the case r equals to 1, in which case this thing is called an invertible sheaf. For reasons that we will not really discuss. And then its total space is a line bundle. And so somehow maybe you have already seen that the vector bundle of rank 1 is also called a line bundle, because essentially all of these fibers are then one-dimensional vector spaces, which are just lines. Okay, so that's maybe a picture to have in mind. And we did see some examples. So one particularly easy one, if you start with the trivial locally free sheaf of rank R, which is just R copies of OX, then as discussed in the proof just now, the total space is actually just this projection here. And this is then also called the trivial vector bundle. One non-example, you should also keep in mind what is not an example of this stuff which you're currently defining. We have seen these skyscraper sheaves, right? They had just this single non-trivial fiber basically at one point. So the sections gave back k if the open set contains this point, and if you look at sections on open set not containing p, then you get 0. And from this definition, you can immediately calculate that the fiber of this f at a point q in x, well, if q is equal to p, then you get exactly k. And if q is not equal to p, just get 0. And from that, we see f is not locally free, because this would, at least if you are in kind of a normal situation where this one point set p is not open, right? So this is then not locally free, because if you are locally free, we have seen then at least on an open neighborhood of this point, all the fibers should be the same dimension. But here we see this dimension 1 and this dimension 0 at all the other points. So in general, this skyscraper sheaf is not an example. And one reason why the locally free sheaves are very nice is that if you do any of these standard operations, at least the ones that we discuss here, if you do any of these operations with locally free sheaves, then you get back a locally free sheaf. And in fact, you can also determine what happens to the ranks. So somehow if f and g are locally free sheaves of ranks m and n on the same space x, then at least in these first cases, so then direct sum is locally free of rank the sum of the m and n. The tensor product is locally free of rank m times n. And the dual, which we have also seen, is locally free of rank the same as the sheaf itself. So this doesn't change. And then finally, if you have a morphism here and f is locally free on x, then its pullback is also locally free of the same rank. Let me here, the proof is just as one idea, and then it's just a lot of notation. So let me just go through it like this. So the crucial idea when you work with locally free sheaves is you choose these trivializing open subsets And then you can, often by shrinking them, you can make different locally free sheaves, in this case, actually trivial, like this. So assume that we have any point inside X. Then our goal is just that for all of these constructions, we want to find an open neighborhood of this point on which the various constructions, like the direct sum, is trivial. And what we do know is that F and G have the property that on such an open cover, we can make them trivial. And so for this point P, on the one hand, we find an open subset U on which F becomes just a direct sum of copies of OU. And we find another subset V on which G becomes such a direct sum of things. And then what you just do if you want to have both of these sheaves play nicely, then you just choose some even smaller affine open subset W, which is contained in both U and V, and such that P is in there. And then if you restrict to this very small subset W, then both F and G become trivial there. And then we just do all these operations. And now the good thing is, because we're such a small subset, so somehow the F restricted to W is then actually just the sheaf associated to M copies of R, like this, right? Because it was already on U given by this direct sum. So it's still given by the direct sum of O spec R to the power M. And this is just the tilde of R to the power M. And then the good thing is all these operations, which we like direct sum, tensor product, and duals, once we are on an affine open subset and we have this one of these tilde modules, then we can perform them just on the module level. So in other words, if we want to take this direct sum, we just take the direct sum of the modules like this and then place a big tilde on it. And so then in this case, for example, it's just clear that if you take M copies of R and then you take direct sum with N copies of R, you get M plus N copies. And then the tilde just gives you O of W to this power. So this explains also why if you start with ranks M and N, you get M plus N here. And then similar here for the tensor product, well, then you just get the same modules, but now you place the tensor product between them. And this is then also just a calculation that the tensor product of this with this module gives you R to the M times N. And so this becomes this sheaf here. And so this is why the ranks are multiplied in the tensor product. And then for the dual, you just use that you can compute the dual sheaf by taking this dual module and then placing the tilde on it. But the dual module of R to the power M is just R to the power M itself again. And the tilde just gives you, again, OW to the power M. So the good thing is that for these locally free sheaves, one of the reasons why they behave nicely is that because we can then restrict all these calculations to an affine open subset spec R and then perform this there. And then finally, there was this situation, if you have a morphism and locally free on the target, then the pullback should be locally free. And for this, you just observe that, well, the target is covered by the spec R on which F is just given by R to the power M tilde. And so the pre-images of these blue things, they cover X, right? Because if these things cover Y, then the pre-images cover X. And then for any point in X, you first find such a blue thing containing it, and then you find a smaller affine open subset contained in there, some spec S, and so then now this red thing, spec S, maps to spec R, and then we're back into the nice affine situation. And then in particular, we can do this pullback. We don't have to do this whole sheavification and so on. We can just do it on the module level, right? Because f on spec R is given by this R direct sum M. And then pulling back just means we tensor over R with S, but then tensor product and direct sum are nicely compatible. We can first draw out this direct sum, and then we have R tensor over R with S. But this we have already seen, R tensor over R with S is always isomorphic to S. So this tensor product just becomes an S to the direct sum M. And this is exactly what we wanted. So somehow this pullback is isomorphic to structure sheaf to the power M. And this concludes the proof. So yeah, somehow these locally free things behave really nicely because exactly on these affine open covers, we can make them very easy to handle. And then things like the dual and these tensor products work very nicely. Okay. So this was about the locally free sheaves, and then we conclude this chapter with an actual application, which maybe for the first time shows a bit like why is it useful to think about all these sheaves and these OX modules, because it answers the very concrete questions about projective spaces that we could have asked much earlier. Okay, so this is the next and the final one in this chapter here.